Inside a material science laboratory in Shenyang, a machine slowly draws out a fiber thinner than a human hair, spun not from cotton or silk, but from tens of thousands of hollow carbon cylinders, each only a handful of atoms wide. And when researchers finally run a current through it, the number that comes back on the display is one that copper wire has never touched. That is real. It exists. It's been published in a peer-reviewed material science journal, and it represents the end of a technical dead end that had frustrated scientists on nearly every continent for more than 20 years. Before this video is over, you're going to understand exactly why copper, the metal that built the entire electrified world, is quietly running into a wall it can't engineer its way past, why a piece of carbon a billion times thinner than a strand of hair might be the thing that finally replaces it, and why this specific Chinese breakthrough only worked after decades of nearly everyone else's attempts had failed. Every figure in this video comes from a peer-reviewed study, direct statements from the research team, and specialist science journalism covering the actual published data. Cross-checking record-setting conductivity numbers that get exaggerated constantly online took real effort, so if that's useful to you, hitting like and subscribe genuinely helps this channel keep doing that kind of digging properly. By the end of this video, you'll understand exactly what this wire can already do, and just as importantly, what it genuinely can't do yet. Here's where this story actually has to start, and it isn't in a lab at all. It starts with a metal that has quietly run the modern world for more than a century without anyone giving it much thought. Copper carries electricity through nearly everything humans have built since the age of electrification began. Household wiring, power grids, undersea internet cables, the windings inside every electric motor, and the battery-to-wheel connections inside every electric vehicle currently rolling off a production line anywhere on Earth. Here's the thing about copper that most people never think about. It isn't chosen because it's the best conductor theoretically possible. It's chosen because, historically, nothing else has offered a comparable mix of high conductivity, workability, and cost all at once. Think about what that actually means for a second. An entire civilization's electrical infrastructure has been built around the practical limitations of one specific reddish-brown metal, not because it's perfect, but because for 100 years, nothing better has been buildable at any meaningful scale. Here's where that quiet dominance starts breaking down. Global demand for copper is now surging on multiple fronts simultaneously, driven by the explosive growth of electric vehicles, renewable energy grids, and data centers. At exactly the same moment, mining companies are warning that the easiest, richest copper deposits on the planet have already been found and dug up, leaving increasingly expensive, lower-grade ore behind. Copper is also heavy, dense enough that every kilometer of copper wiring strung across a power grid or wound into a motor adds real, unavoidable weight that costs fuel in an aircraft, costs range in an electric vehicle, and costs money everywhere that has to be transported or lifted. That weight and scarcity problem is exactly the opening an entirely different class of material has spent over 2 decades trying to walk through. Here's the material that's been waiting in the wings this entire time. The carbon nanotube, a cylindrical molecule built from carbon atoms linked together in a repeating hexagonal pattern, with a diameter as small as a single nanometer. For comparison, an ordinary strand of human hair measures roughly 100,000 nanometers across, meaning a single carbon nanotube is thinner than a hair by a factor of 100,000. Here's the property that made scientists obsessed with this material the moment it was discovered back in 1991. Carbon nanotubes are around 100 times stronger than steel of the same size, while weighing only a small fraction as much, and individual nanotubes have demonstrated electrical conductivity that can genuinely rival or exceed copper at the microscopic scale. Think about what a material like that could theoretically do if it ever reached usable size. Wiring that weighs a fraction of what copper weighs, strong enough to double as structural support instead of needing separate framing, conducting electricity just as well or better. Here's the problem that kept the theoretical promise locked inside laboratory curiosities for more than 2 decades. An individual carbon nanotube is a molecule, not a wire, and figuring out how to bind tens of thousands of these microscopic tubes together into one continuous usable fiber without destroying the very properties that made them special in the first place turned out to be a genuinely brutal engineering problem, one that took the global research community more than 20 years to actually solve. Here's why that binding process is so difficult. Every time researchers tried to pack nanotubes together into a larger fiber using earlier spinning techniques, the individual tubes ended up poorly aligned and loosely connected, creating gaps and weak contact points between them that acted like tiny roadblocks, forcing electrons to hop across resistance-heavy junctions instead of flowing smoothly the way they do inside a solid metal wire. Read that again. The individual building blocks were nearly perfect, but every attempt to assemble them at any usable scale quietly threw most of that perfection away. That 2-decade bottleneck is exactly the wall the team in Shenyang finally found a way through. Here's the team behind the actual breakthrough. Scientists at the Shenyang National Laboratory for Materials Science, operating under the Institute of Metal Research within the Chinese Academy of Sciences in Liaoning Province, led by researchers Liu Chang and Ho Pengxiang, published their findings in the peer-reviewed journal Advanced Functional Materials. Here's the mechanism behind what they actually changed. Rather than inventing an entirely new spinning process from scratch, the team took a widely used existing method known as dry jet wet spinning, in which nanotube material is drawn through a small air gap before being pulled into a coagulation bath that helps the fiber solidify, and engineered a new device specifically designed to compact and align the nanotubes with dramatically more precision during that critical spinning stage. Here's what makes that precision improvement genuinely significant rather than a minor tweak. The team specifically worked with what are called double-walled carbon nanotubes, a slightly more complex structure than the simplest single-walled version, and successfully spun long, high molecular weight nanotubes through a carefully stabilized air gap, achieving a level of alignment and packing density inside the finished fiber that earlier spinning attempts simply hadn't been able to reach. Think about what better alignment actually does at the physical level. When nanotubes sit closely packed and pointing in nearly the exact same direction, electrons can travel through far more of the fiber's length without hitting a poorly connected junction, which is precisely the defect that had capped every earlier generation of carbon nanotube fiber's real-world performance well below its theoretical potential. Here's the number that made this a genuine scientific record, rather than just an incremental improvement. The resulting double-walled carbon nanotube fibers achieved an electrical conductivity of 1.1 times 10 to the 7th Siemens per meter, officially described in coverage of the published research as record-breaking for this class of material. Here's what that number actually means in plain terms. Siemens per meter measures how easily a material lets electrical current flow through it, and reaching this level places the fiber's conductivity in genuinely serious rivalry with copper itself, a metal whose own conductivity sits close to 5.8 times 10 to the 7th Siemens per meter, meaning this fiber isn't simply pretty good for a carbon material. It's now operating in the same performance category as one of the best natural electrical conductors humans have ever used. But raw conductivity alone doesn't tell the whole story. And here's the second number that matters just as much. The fiber can carry a current density of 8 times 10 to the 8th amperes per square meter, officially confirmed in the published research as a high current carrying capacity, meaning the wire doesn't just conduct electricity efficiently, it can also handle a genuinely large amount of current flowing through it without failing, a critical requirement for any material that hopes to eventually replace copper in real power transmission applications, rather than staying confined to delicate, low-current lab demonstrations. Think about what carrying that much current through something this thin and light actually represents. A fiber engineered at a scale thinner than a human hair, handling current density figures that put it in the conversation with industrial-grade metal conductors, not far behind them anymore. Here's the part of this story that matters just as much as raw electrical performance. The same fiber also demonstrated a tensile strength of 1.65 gigapascals, alongside a toughness measurement of 130.9 megajoules per cubic meter, officially described in the published findings as among the best results ever recorded for a wet-spun carbon nanotube fiber. Here's why strength matters just as much as conductivity for a material trying to replace copper specifically. Ordinary copper wire is a genuinely poor structural material. It's soft, it stretches, and it needs external support structures, insulation, and protective sheathing to survive real-world installation and use, all of which adds weight and cost on top of the copper itself. A fiber this strong, by contrast, can begin to double as its own structural support. Carrying mechanical load at the same time, it's carrying electrical current, exactly the kind of dual-purpose engineering that becomes enormously valuable the moment weight starts to matter as much as conductivity does. Here's where that weight advantage becomes almost impossible to ignore. Carbon nanotubes have a density of roughly 1.3 to 2.1 grams per cubic centimeter, depending on their exact structure, compared to copper's density of nearly 9 grams per cubic centimeter. Meaning, kilogram for kilogram, a carbon nanotube fiber conductor can weigh somewhere around 4 to 7 times less than a copper wire, delivering comparable electrical performance. Think about what a 4 to 7-fold weight reduction actually means once you scale it up to something like an aircraft's wiring harness, a satellite's power system, or a long-distance power transmission line stretching across hundreds of kilometers. Weight that used to be locked in as an unavoidable cost of using copper suddenly becomes something engineers can meaningfully reduce. Before going any further into what this specific breakthrough could eventually unlock, it's worth pulling back and understanding why China's research institutions specifically have ended up at the center of this entire global race. According to specialist science journalism covering the field, China has positioned itself at the forefront of both carbon nanotube fiber research and the practical optimization work needed to turn laboratory promise into a genuinely usable material, with the Shenyang team representing one of several separate Chinese research groups actively working on different pieces of the same underlying materials science puzzle. Here's the thing that makes that concentration of effort significant. This same Shenyang laboratory hasn't stopped at pure carbon nanotube fiber. The same research group has separately published work on carbon nanotube and copper core shell fibers, a hybrid design where a thin copper layer is deposited directly onto the surface of a carbon nanotube fiber core, and that hybrid material demonstrated a specific electrical conductivity, meaning conductivity measured per unit of weight rather than per unit of volume. That came in 56% higher than pure copper's own specific conductivity. Think about what running two parallel research tracks at once actually signals. This isn't a single lucky lab result. It's a broader, sustained material science program deliberately exploring multiple different paths toward the same destination, pure carbon nanotube fiber on one track and copper-carbon hybrid fiber on another. Precisely the kind of diversified, well-funded research strategy that tends to actually produce commercially viable materials, rather than isolated academic curiosities that quietly disappear after one press release. This is not a single research paper happening in isolation. It's a sustained, multi-year national materials science effort, and once you see it at that scale, the applications this breakthrough is already being positioned for start to look a lot less speculative and a lot more like a genuine industrial roadmap. Here's where this technology is specifically being aimed according to the research team's own stated ambitions. Aerospace and other critical industries, alongside energy storage applications, sit at the top of the list. And it's not hard to see why once you think through what weight actually costs in those specific sectors. In an aircraft or a satellite, every kilogram of wiring is a kilogram that either has to be lifted at enormous fuel or launch cost, or a kilogram that could otherwise have gone toward payload, fuel reserves, or mission-critical equipment instead. Here's the thing that makes electric vehicles a particularly natural fit for the same logic. EV manufacturers are already fighting an intense, well-documented battle to shave excess weight out of every component they can, specifically because a lighter vehicle directly extends driving range on a fixed battery size, and copper wiring inside an EV's motors and battery connections represents a meaningful chunk of a vehicle's total weight that a fiber conductor 4 to 7 times lighter could directly attack. Here's a genuinely striking possibility mentioned in coverage of related carbon nanotube research. Some of the same underlying nanotube fiber technology has even been discussed in the context of space elevator concepts, structures that would require cabling strong enough and light enough to stretch from the Earth's surface into orbit, a use case so extreme that it only makes sense to even discuss once a material's strength-to-weight ratio starts approaching genuinely exotic territory, exactly where carbon nanotube fiber now sits. Think about the range of that application list for a second. From something as immediately practical as EV wiring harnesses, all the way out to something as far future as space elevator. Cabling, and the same underlying material science breakthrough, is being seriously discussed as relevant to both ends of that spectrum. Here's the honest concession we're sitting with before this video wraps up, because credibility matters more than a triumphant headline. This breakthrough, as genuinely significant as it is, remains a laboratory-scale research result published in a peer-reviewed journal, not a commercially available bulk conductor material sitting on a shelf ready to replace copper wiring in your home, your car, or your country's power grid tomorrow. Manufacturing a fiber with record-setting properties inside a controlled research lab is one enormous milestone. But scaling that exact same manufacturing precision up to the kilometers of continuous, defect-free wire that real power grids and vehicle production lines actually require is a completely separate engineering and economic challenge, one that has quietly stalled plenty of previous copper-killer materials, somewhere between an impressive published paper and an actual factory floor. Carbon nanotube, raw material itself, also still costs significantly more to produce at scale than copper does, and closing that cost gap enough to make large-scale adoption economically realistic, rather than limited to premium aerospace and defense applications, where cost matters less than weight, will likely take years of continued manufacturing refinement, even with a genuinely working laboratory breakthrough already in hand. Here's why that caveat doesn't diminish the achievement, though. Every single transformative material in modern industrial history, from the earliest mass-produced steel to today's lithium-ion batteries, went through this exact same multi-year gap between a genuine laboratory breakthrough and affordable, scaled manufacturing, and the fact that Chinese researchers have now cleared the single hardest scientific hurdle. Actually building a macro-scale fiber that preserves most of an individual carbon nanotube's exceptional properties instead of losing them during assembly is precisely the step that had to happen first, before any conversation about factories and cost curves could even begin. So here's the full picture, start to finish. Copper has run the electrified world for more than a century, not because it's the best possible conductor, but because nothing else has been buildable at meaningful scale. And now surging demand alongside increasingly expensive ore is starting to expose the limits of that century-old assumption. Carbon nanotubes offered a theoretical alternative from the moment they were discovered in 1991. But a genuinely brutal engineering bottleneck, binding thousands of individual nanotubes into one continuous, well-aligned fiber, kept that promise locked inside individual lab samples for more than 20 years. A research team at the Shenyang National Laboratory for Materials Science finally cracked that bottleneck by refining the precision of an existing spinning technique, producing a double-walled carbon nanotube fiber with a record-breaking conductivity of 1.1 times 10 to the 7th Siemens per meter, a high current carrying capacity, and tensile strength and toughness numbers among the best ever recorded for this class of material, all while weighing roughly 4 to 7 times less than copper, delivering comparable performance. What you're actually watching in this story is the same shift that happened when synthetic fibers first started challenging cotton and wool a century ago. An established, trusted material that nobody seriously questioned for generations, suddenly facing a genuine engineered alternative, not because the old material stopped working, but because something new finally cleared the specific technical bottleneck that had kept it out of the conversation for decades. Copper isn't disappearing from the world anytime soon, but for the first time in over 100 years, it now has a genuine, laboratory-proven rival, and that rival was just built in a lab in Shenyang. If breakdowns like this, the real research and the real numbers behind China's biggest materials science pushes, are useful to you, hit like and subscribe, because there's more of this coming, including a closer look at what happens the first time carbon nanotube conductors actually make it into a commercially available product rather than a peer-reviewed paper. So here's the honest question for the comments. Does a laboratory material this promising make you think copper's dominance is genuinely numbered within our lifetimes? Or does the scaling and cost gap between a lab breakthrough and an actual factory floor make you think this is still further away than the headlines suggest? I read every single one.